now that you guys know about Lewis structure, formal charges, drawing organic molecules, now we gotta think more about the electron distribution of these molecules and the geometry of these molecules. I'm gonna complete the Lewis structures of this compound that I drew here. And then I'm gonna ask a question which we are gonna answer together, which is what's the so we're gonna answer the question, what is the hybridization of, and I'm gonna point the atom that I want you guys to tell me, and then so I'm gonna point toward this carbon over here, okay? So what's the hybridization of that carbon? Okay, sp3. So remember, very quickly, I'm going to make a couple of summary points here that I want you guys to really understand and remember basically from previous class. So remember, guys, we defined in last class, we talked about sigma bonds. So anybody remember what is a sigma bond? How did we define in class a sigma bond?
Sigma bond is when we have a single bond, right?
Well, that's not the definition of a sigma bond. So when we have, see, that's a good example for me. What you said is correct. When there is only a single bond, that bond is sigma. But that's not the definition of a sigma bond. Okay, so it's very important to analyze the questions when we give an answer. Somebody says cylindrically unsymmetrical. That is also correct, but that's not the definition. That's what sigma bond stands for. Okay, so it's the direct overlapping of atomic or hybrid orbitals. Okay, that's correct, Jennifer. Beautiful. Okay, so that's the definition, guys, of a sigma bond, and I'm going to show you over here because that's so important for me that you guys really know. And more than you don't have, once again, I don't want you guys to memorize anything. I just want you guys to really understand what that is, right? So let's say this is a hybrid orbital, and let's say we have another hybrid orbitals here. So when these two atoms, these two hybrid orbitals form a sigma bond, this is a sigma bond, direct overlapping of two hybrid orbitals, okay? So there is electron density across the axis of both atoms. That's the definition of a sigma bond, direct overlapping. So both orbitals are in touch. The electrons are in between the two nuclei of both atoms. That's the definition. And once again, you can directly overlap either atomic or hybrid orbitals, which you already know what they are. And we also talk about pi bonds. Anybody remember what was the definition of a pi bond? And type it on the chat. Anybody remember what's our definition? How did we define in class a pi bond?
So we have double bond.
That's once again, that's a correct. That is correct, but that's not the answer to the question because that's not the definition of a pi bond. So some Iman said beautifully, side-by-side overlapping of pure p orbitals. So that's beautiful. So guys, couple of things about the difference in these two. Okay, so you gotta really understand. First of all, the sigma is direct overlapping. The pi bonds is side by side. That's the number one thing. I am missing something in that definition that I mentioned in class. Anybody remember what am I missing? I'll go over that now. No, I explained that in the previous class, but I will review that again today. Anybody remember what else am I missing in the definition of a pi bond? Side-by-side overlapping of p orbitals, and what else do I need? This is a side-by-side overlapping, right? This is a direct overlapping. I'm gonna write it over here so you physically see what it is. What else did we talk about the pi bonds?
But they're also parallel and supposed to be in the same plane.
Correct. So that's beautiful. That's so they need to be properly aligned. Okay. So that I show you here on the screen what is direct and overlapping and what is the side-by-side overlapping. So it's important for you. That's the first difference in between a sigma and a pi. Okay. And the second difference is the orbitals that are forming the bonding. In the sigma is direct overlapping of either atomic or hybrid orbitals. For the p orbitals, side-by-side overlapping only of pure p orbitals. Only p orbitals can form pi bonds, guys. Please remember this. That's so relevant. And they must be properly aligned, meaning that they must be parallel and in the same plane. Okay. So this is a side-by-side overlapping of two p orbitals. So how does a pi bond looks like? It looks like this. I'm going to show you right now. So you can see physically what I mean by all these ideas. So I want you guys to picture that in 3D as well. Okay. So this is the result. This is a side-by-side of the result of a side-by-side overlapping of pure p orbitals. Okay. So look at the difference. Electron density up here and down here, okay, above and below. Here is one nuclei, here is another nuclei. In the sigma bond, the electron density is right in the center in between these two nuclei, so right here. Okay, in the pi bond, the electron density is above and below the plane of the molecule. Okay, that's a major difference in between a sigma and a pi bond. All right. So with that in mind, let's go back to the idea of hybridization again. And I was asking, what is the hybridization of the carbon that I pointed with the arrow there here? And the answer was sp3. So once again, I'm going to quickly remember you guys how we learned that in the previous class, because this is once again something very important to understand. So how many orbitals in the valence shell of carbon? How many orbitals in the valence shell of the carbon atom? 4 orbitals. So 1s and 3p orbitals, correct? So we have the 2s orbitals, and the 3 2p orbitals, x, y, and z, right? Everybody knows that at this point. And we have 4 electrons in the valence shell, something that everybody also knows. So this is basically the electron distribution of the valence shell of carbon. So that's pretty simple. Nothing new here. 2, 3, 4 electrons. Okay. So remember how I said in class that before carbon forming any bonds to any other atoms, any sigma bond, okay? And I'm going to emphasize that before forming any sigma bonds, because the pi bonds are the result of pure orbitals. So before forming any sigma bonds, the atomic orbitals of carbons will be hybridized. And the orbitals that the carbon is using for the bonding are hybrid orbitals. So if we combine 1s and 3p, so if we combine 4 atomic orbitals, how many how many hybrid orbitals do we get? If we combine 4 atomic orbitals. So we always get the same number, right? So the same number of atomic orbitals that we combine, the same number of hybrid orbitals we get. Something we also went over in the previous class. So if we combine 4 atomic, we'll get 4 hybrid. No secrets with that. And those 4 hybrids, we are going to call it. So since we are combining 1s and 3p, we are forming 4sp3. Okay? So that's what's happening before bonding. And these 4 sp3 hybrid orbitals are the orbitals that the carbons will use for bonding to any other atom. So the 4 bonds of the carbon atom will be the result of the carbon using 4 hybrid orbitals. Obviously, there are 4 electrons in the valence shell of carbon, meaning that clearly each electron will be in 1 hybrid orbital. Okay, so guys, that means that you can see how here, okay, we have 4 hybrid orbitals, 4 bonds for carbon. So this carbon that I'm pointing on the arrow has, how many hydrogens do we have here? How many hydrogens on that carbon? 3 hydrogens, right? So I want you guys to tell me. I'm gonna write a question. What are the orbitals participating in the carbon hydrogen bonds of the atom that I'm pointing with the arrow? What are the orbitals participating in the carbon hydrogen bonds of this carbon over here? Okay, so that's one really good answer. Everybody agrees with Galena, or any other answers? What are the orbitals participating in the carbon hydrogen bonds of this carbon here? So you think about the carbon hydrogen bonds, guys. Once again, for the carbon before carbon bonding, what is happening? Hybridizing orbitals. Okay, so the carbon, this carbon that I'm pointing here, has 4 hydrogen orbitals for bonding. Okay, 3 of these hybrid orbitals will be used to bind 3 hydrogens. Okay, and the 4th hybrid orbital will be used to bind to this carbon over here. So now I'm going to show you, ask you another question. So what about this sigma bond here? What are the orbitals participating in that sigma bond? Okay, what are the orbitals? I want more people answering that question. What are the orbitals? And if you guys don't understand, please ask. It is extremely important that everybody. So what exactly do you don't understand, Jennifer? You can speak on the microphone if you want to. And again, not judging here. I can repeat the answers 1,000 times if you guys require. It doesn't matter.
I don't understand how to answer this question specifically. What are
Okay,
the
so what?
orbitals participating?
So what exactly do you don't understand? Do you understand the question in the first place? Because that's the most important thing, right?
Yeah.
So what does the question means exactly? What are the orbitals participating in this sigma bond? A sigma bond is a result of how many orbitals? How many orbitals are making a sigma bond? Look at the definition here. Direct overlapping of atomic or hybrid orbital. This is a direct overlapping. So how many orbitals make a bond? Guys, a bond is a result of the overlapping of how many orbitals? Because I think that's what a lot of people might be missing, okay? A bond, a sigma bond here, or any bond, how many electrons in a bond? 2 electrons, right? And so a bond, a sigma bond, is the result of the side-by-side overlapping of 2 orbitals. They could be hybrid or they could be atomic, okay? In this case, they are both hybrid. So 2 orbitals are participating in a sigma bond. Why is that? Because each atom contributes with 1 orbital. So how can you even envision this better? So let's assume this carbon, as I said, is going to hybridize its atomic orbital before bonding to anything else. 4 hybrid orbitals. So the first 3 hybrid orbitals, these 3 are going to be used for bonding to hydrogens. And the 4th hybrid orbital, this carbon is going to use it to bond to the carbon atom. Because again, how many bonds do we have in that carbon? In any carbon? 4 bonds. Okay, so this carbon atom needs 4 orbitals because it's bonding. It has 4 bonds. one orbital per bond, okay, from each atom. So this carbon atom is using has four bonds, is using 4 orbitals for these 4 bonds, the 4 sp3. 3 sp3 will be used for 3 hydrogens, one per each, one hydrogen bonding through this orbital, one here, one here. And the fourth is going to be an sp3 hybrid orbital bonding this carbon here. So this is a sigma sp3, which basically means that sigma bond is the result of the side-by-side overlapping of an sp3 orbital from this carbon and an sp3 orbital of this carbon here. Okay, the remaining this CH bond here, I'm gonna write it just in case it's not clear for everybody. I'm sorry. So this sigma CH so once again, this sigma CH, how many orbitals are participating in this sigma bond here, guys? CH bond, how many orbitals are participating there in that bond? 2 orbitals, perfect. 2 orbitals, okay? So one from each atom. The carbon is, which orbital is the carbon providing for that sigma bond? The carbon is providing an sp3 orbital. Beautiful. And what about the hydrogen? What orbital is the hydrogen providing for that bond? Is the 1s orbital, because there is only one orbital in hydrogen. So that's a sigma sp3s. So that could be something like this. I'm going to show you exactly what I mean by that. So everybody can follow exactly the idea. So this is a sp3. I'm going to actually point it in the direction of the bond. It's an sp3. And the S will look like this. Okay, so this is a sigma sp3s. Okay, now this bond here, I'm gonna color code this because it's getting a little confusing, just in case. So that color is not good. Okay. Okay, the sigma bond color blue is how many orbitals are participating in that sigma bond? In the blue color sigma bond, how many orbitals are participating in that sigma bond? Okay, 2 orbitals. Any other answer, guys? I want to make sure that everybody's paying attention. How many orbitals are participating in the sigma bond that is color code with a blue color on the screen? How many orbitals are participating in that bond? 2 orbitals are participating in that bond. One is an sp3 from the carbon, and because this carbon is sp3 hybridized, that's also an sp3, so it's a sigma sp3 sp3. So what you have to know is you have to assign hybridization to every atom in the molecule, and that will allow you to determine what are the orbitals participating in each bond. Okay, so let's see if you really guys understood this. I'm gonna look now at this oxygen here. Do the orbitals change if there is a double bond? They do change, and we will see that now in a few minutes. Okay, let's focus on for now, let's focus on atoms having only single bonds. Okay, because then we increase the complexity. So I want to focus on this oxygen over here. All right, so my first question about that oxygen is, what is the hybridization of the oxygen? I'm sorry, well, see, what's the hybridization of the before I said that, I'm going to ask you guys, in this oxygen here, do we see any pi bonds in that oxygen? No pi bonds in that oxygen, right? So if there is no pi bonds in that oxygen, what is the hybridization of that oxygen if it has no pi bonds? Okay, if there is no pi bond, should there be any p orbitals used for pi bonds? No, because there is no pi bonds, right? So what would be the hybridization of that oxygen if there is no pi bonds? Okay, so let me show you here. Oxygen is in group 6. How many how many orbitals in the valence shell of oxygen? How many orbitals in the how many orbitals? That's how many electrons, how many orbitals in the valence shell of oxygen? 4 orbitals, shell 2, right? And we have 6 electrons. So I wrote 2 electrons there, 2, 3, 4, 5, 6. Okay? 6 electrons the valence shell of that oxygen. Okay? All right, so if this oxygen has no pi bonds at all, there is no orbital that must be safe for any pi bondings because there is simply no pi bonds, right? So how many orbitals are we going to hybridize here for this oxygen? What's the total number of orbitals that we are going to hybridize for this oxygen? Atomic orbitals. All of them, because since there is no pi bond, we don't need to separate any p orbital for pi bonds. No pi bond whatsoever. So we're going to hybridize the 4 orbitals. And if we hybridize 4 orbitals, we get 4 sp3 hybrid orbitals. Do you see any multiple bonds here, Rachel? Do you see any double bonds here? That's why there is no pi bonds. Okay, so we hybridize 4 orbitals because this oxygen has only single bonds. That's the point. In this oxygen, I see 2 single bonds and 2 lone pairs. That's it. So no pi bonds, all single bonds in one atom, every atom with all single bonds, and there is an exception to this. I'm going to talk about this in 15 minutes or so, okay? But for now, let's talk about the general rule, which is once you look at any atom, it doesn't matter if it's not carbon, any atom having only single bonds will be always sp3 hybridized, okay? Always it will be sp3 hybridized. So in the case of oxygen, okay, once again, no pi bonds in this oxygen, so oxygen is gonna hybridize its 4 atomic orbitals, getting 4 sp3 hybrid orbitals. Now we have 6 electrons because oxygen has 6 electrons in the valence shell, meaning that we are gonna then add them 1, 2, 3, and 4. 5, 6, right? 6 electrons in the valence shell. So 4 hybrid orbitals, 6 electrons, and now my question is, guys, how many hybrid orbitals oxygen can provide for bonding? It can provide only 2 because the other 2 hybrid orbitals are already full. It cannot be shared with any other atom. So what are these 2 here? The ones that are full already, what are they used for? In the oxygen atom. Look at the oxygen here with the Lewis structure. What are these 2 hybrid orbitals having? The lone pairs. Exactly. The lone pairs. So 4 hybrid orbitals because this oxygen, once again, only single bonds is sp3 hybridized. The moment, so this is maybe this is going to be easier for you to remember. So it's the only single bonds, sp3. Okay. And guys, whenever we talk about sp3 hybridization, how many orbitals are we talking about? How many hybrid orbitals? 4. Always. Okay? So that's what you need to, that's all you need to know. So I look at the atom, I see all single bonds, I know that's sp3 hybridized. And the moment I know it's sp3 hybridized, I know there are 4 hybrid orbitals, 4 sp3 hybrid orbitals. So in this oxygen, one of the sp3 hybrid orbitals is going to be used for this sigma bond, another one for this sigma bond, and the other 2 will contain the lone pairs. Okay? Everybody's understanding that? And if you don't, please let me know. This is very important. So if I ask you in this molecule, in which orbitals, I'm going to type it on the chat, in which orbitals are the lone pairs located? What's the answer to that question? Where are the lone pairs located for that red oxygen? Which type of orbitals are these lone pairs filling up? sp3 hybrid orbitals, correct. Because that oxygen is sp3, okay? And because that oxygen is sp3, it has 4 sp3 hybrid orbitals, 2 for sigma bonds and 2 with the lone pairs. What is the geometry of an sp3 hybridized atom? It's a tetrahedral structure. That's the geometry of any sp3 hybridized atom, okay? And it's just like that right here. I'm gonna rotate it so now you can see better. So imagine that this is your oxygen atom right here. You will have 1 lone pair here in an sp3 hybrid orbital is coming toward you, 1 lone pair on the back in an sp3 orbital behind the screen, 1 sigma bond here with another sp3 orbital, another sigma bond here with another sp3 orbital. Okay, that's how the orbital of this oxygen looks like. That oxygen is tetrahedral. So what is the angle in between the lone pairs? What's the angle in between the lone pairs of oxygen? 109.5. Slightly less because they actually repel each other, so it's going to be about 107. But if you say 109, I'll be okay. Okay. So what's the angle in between the lone pairs of the oxygen atom in this molecule? Is going to be 109.5. Why? Because that oxygen is sp3 hybridized, and the lone pairs are in sp3 hybrid orbitals. Exactly. Every atom is going to hybridize before bonding to carbon or in between them in organic molecules, okay? All right, so I want to focus now. So what about this carbon, guys? What is the hybridization of this carbon atom here? This one over here. What's the hybridization of this carbon? It's sp3 because it only has single bonds, okay? What's the geometry of this carbon? Tetrahedral, okay? So guys, what are the orbitals participating in this bond here, in that sigma bond? What orbitals are participating in that sigma bond? It's a sigma sp3 sp3, okay? It's a sigma sp3 sp3 because both carbons forming that bonding are sp3 hybridized. That is correct, okay? Let's see if you really so if anybody is missing something, please type the question on the chat. I'll be happy to address any questions that you guys might have. So let's focus on this nitrogen here, the purple nitrogen, okay? Okay, so what is the hybridization of that nitrogen? So to answer that question, because here that's so relevant. Okay, You don't need to memorize anything because you gotta reason the questions, okay? And this is how you reason this question. So if I am asked what is a hybridization of this atom, doesn't matter which one. What I'm gonna look is what are the bonds of this atom? If all I see is sigma bonds, I know this atom is sp3 hybridized. Okay? Okay, so in this molecule, everything is sp3 hybridized. Copy. In this molecule, okay? So guys, this nitrogen is sp3 hybridized. Now my question is, in which orbital is the lone pair of nitrogens located? This lone pair, where is it located? Which orbital is using for the nitrogen to hold these two electrons? So Ruth, it doesn't matter. What determines if the hybridization if whether or not you have double or triple bonds. So what you have to focus is, do I have all single bonds or do I have double or triple bonds? If I see all single bonds, the atom will be sp3 hybridized. There is one exception for that. We will talk about that in a few minutes, okay? So in which orbitals is the lone pair of the nitrogen located? I'm gonna type it on the chat. In fact, you know what, I'm gonna do a polling because I wanna make sure that you guys are paying attention and I wanna get a sense of how is this going. Okay, so in which orbital is the lone pair of nitrogen located? Please answer the question. So in which orbital? Is it in a p orbital? Is it in an s orbital? Is it an sp3, sp2, in an sp? What do you guys think? And the most important thing that I want you guys is to ask yourself how, and this is so important that you follow this. Ask yourself, how do I answer this question? Don't guess. So if I'm asked where are the lone pairs located, what is the next question that I should know to answer that question? What exactly should I know to answer that question? Can anybody answer that? So if I want to know where is the lone pair, what is the hybridization of the atom? That is exactly the point. And once I know the hybridization of the atom, I can understand where are the bonds and the electrons of these atoms located. First of all, I must know what is the hybridization of the atom. So I asked a few minutes ago, what is the hybridization of that nitrogen? Everybody knew that it was sp3 hybridized, right? So if the nitrogen is sp3 hybridized, it has only single bonds, so it's sp3 hybridized, and we talk about 4 hybrid orbitals, okay? All right, so how many bonds do we have in that nitrogen? How many bonds in that nitrogen? 3 bonds, right? 3 bonds. So 3 bonds, and what else do we have in the nitrogen? And a lone pair. So the nitrogen has 3 bonds and a lone pair, right? So 3 bonds and a lone pair, that's total. How many orbitals do I need for that nitrogen? I have 3 bonds and 1 lone pair. How many orbitals do I need? 4. And how many hybrid orbitals do I have? 4. That's perfect. So 3 bonds and a lone pair. So the 3 sigma bonds will use 3 hybrid sp3 orbitals, and the lone pair will be in the remaining sp3 hybrid orbital. Okay, because once again, the reasoning that I'm following is I look at the atom, I see that everything is single bonds. So if all is single bonds, I know it's sp3 hybridized. The moment I know it's sp3 hybridized, I must know that there are 4 hybrid orbitals. In this case, 3 will be used for 3 sigma bonds, and the 4th for the lone pair. So in which orbital is the lone pair located? In an sp3 hybrid orbital, okay? So what is the angle in between the lone pair and this sigma bond here? What's the angle between the lone pair and this sigma bond here, guys? One oh 9.5, because the nitrogen is sp3 exactly, because the nitrogen is sp3 hybridized. Exactly, okay? So everybody must understand that nitrogen is gonna have, and I'm gonna make a drawing slightly different so you guys can record it over here. So in order for you to understand that this is, these are the lone pairs of oxygen, and I'm gonna do the drawing for, I'm gonna draw it like this so you can distinguish the lone pairs between the sigma bonds, okay? So we said the oxygen has 2 lone pairs, they are both in sp3 hybrid orbitals because that oxygen is sp3 hybridized. So the lone pairs are right here. And the angle, we just discussed, that is 109.5. For the nitrogen, we have 3 bonds and a lone pair, 3 sigma bonds and a lone pair. So 3 sigma bonds, and the lone pair will be also in an sp3 hybrid orbital. So that's how the nitrogen is going to look like. Okay. So bottom line being is, whenever you look at an organic molecule, not only carbon, but also oxygen, nitrogen, sulfur atoms, if there are not pi bonds, the atoms will be sp3 hybridized. There is an exception to that. I repeated several times. We're going to see that now. But except for that case, whenever you see all single bonds, it's going to be sp3 hybridized. Why is this angle greater than the why? So why I don't understand the question, Rachel. What's the angle in your opinion for the oxygen atom? So I can address that question, Rachel. So what's the angle in the oxygen? Okay, so yes, because what I said is slightly less. If you said 109.5, I'll be okay. But in reality, electron lone pairs they repel one another, so the molecule is a little bent. Okay. So it's slightly less than 109.5 because of that. There is repulsion between the clouds of electrons here, greater than here, okay? Because this is 2 lone pairs and this is a lone pairs and sigma bonds, okay? But if you said 109.5, I'll be totally okay with that. Any questions? Because we're gonna now jump to the next case. Any questions, guys, in regards to this? Okay, all right, so let's see the next case. Okay, let's look at this molecule here. Okay, let's complete. First of all, we're gonna draw the Lewis structure of the molecule. So I'm gonna add, for an oxygen, I have to add 2 lone pairs. Once again, oxygen is in group 6, 6 electrons in the valence shell. I see 2 bonds here, 2 electrons, so I'm missing 4, 2, 4. Same thing here, 2 bonds, so I'm missing 4, 4. Nitrogen, 3 bonds here, is in group 5, so it's missing 2 electrons, 1 lone pair. So that's the Lewis structure for this molecule, okay? I'm assuming at this point everybody is really good at this, okay? All right, so I'm going to point toward this carbon atom here. How many hydrogens do we have here, guys? How many hydrogens do we have here?
3.
2 hydrogens, right? 2 hydrogens. Okay. In this double bond, how many sigma bond do we have in this double bond? How many bonds are sigma in the double bond? 1 is sigma. And the second one is what? So whenever we have a double bond, one bond is going to be sigma and the second one is going to be pi. Correct. So one bond is going to be sigma. I'm going to write it over here. And the second bond is going to be pi. All right. Remember that I said pi bonds side by side overlapping of pure p orbitals properly aligned. Okay. So I'm going to copy again the electronic distribution of carbon, and I'm going to make the same reasoning that I did before. So this is the electronic distribution of carbon. 4 electrons, 4 orbitals in the valence shell. So for the sigma, and I'm gonna, now that we have, because it was all sigma bonds before, okay? So when I look at this carbon here, okay, I have a sigma bond and 1 pi, and a pi bond. So how many orbitals from the valence shell this carbon will have hybridized? How many will have available for hybridization from the atomic ones? 3 only will be available for hybridization, because the 4th, which is a p orbital, must be used for what? For the pi bond, right? So we're going to save 1 p orbital for the pi bond, because we know that a pi bond is side-by-side overlapping of pure p orbitals. And we're hybridizing the remaining 3. So if we hybridize 3, we get 3 hybrid orbitals. And in this case, we're going to call them, as I said in the previous class, sp2, because we're hybridizing 1s and 2p. Okay? That's sp2. 1s and 2p, that's a total of 3, sp2. So whenever we see an atom with double bonds, so means that it has 1 pi bond. And if there is 1 pi bond, this atom will be sp2 hybridized. Okay? Is that clear? So this carbon is sp2. This carbon is sp2 because only 3 atomic orbitals can be hybridized. The 4th is used for the pi bond. Okay? So I'm going to say this carbon atom is sp2. Guys, remember the geometry of, before I go into that, so I'm going to repeat the exercise that I did before. So in this case, I'm going to say, one double bond, that's going to be sp2. Okay? And then I will have 3 hybrid orbitals, big and a p orbital. One double bond, I know the atom is going to be sp2 hybridized. And the moment I know it's sp2 hybridized, I must know that that atom is going to have 3 hybrid orbitals, so 3 sp2 and 1 pure p orbital for the pi bond. Hydrogen cannot be hybridized. How many? Okay, so no, how many atomic orbitals in hydrogen? No, how many? 1. So can you talk about hybridization in hydrogen if it's only 1 atomic orbital? No, because there is nothing to hybridize with. It's just 1 orbital, okay? So once again, I'm gonna repeat this reasoning because I really want everybody to understand this. This carbon is sp2 because it has a pi bond, a double bond. The moment I see 1 double bond, I'm gonna assign sp2 hybridization. And when I assign sp2, I understand that there are 3 sp2 hybrid orbitals and 1 p orbital. The moment I know it's sp2, I know there are 3 sp2 hybrid orbital and 1 p orbital. So this sigma bond that I am showing here, what are the orbitals participating in that sigma bond? CH. Which orbitals are participating here? Jennifer or anybody else, come on. See, I wanted to see, guys, if you really understood this. So what are the orbitals participating in this CH bond? 1 sp, so the carbon is participating with an sp2 and the hydrogen with an s. So this is an sp2 s sigma bond. Okay. So the other thing that I want you guys to really understand, the geometry of sp2 hybridized atoms is trigonal planar. The angle is 120 degrees. The angle obviously between the sigma bonds is 120 degrees, right? And this is how the molecule is going to look like. I'll show you over here. So both carbons are sp2. 120 degrees in between these two. 120 degrees in between these two. 120 degrees in between these two. Okay? And there is an electron density cloud above and below the plane of the molecule because the molecule is trigonal planar. That is the pi bond. Okay? So this is how, if I were to draw this, you would be putting the angle. That's how this section of the molecule will look like. Trigonal planar. 120 degree angle here and cloud of electrons above and below the plane. That's a pi bond. What about this sigma bond here? What kind of orbitals what are the orbitals participating in this sigma bond? So Iman asked, in a sigma bond, can you repeat where the electron density is? Yes. Sigma bond, Iman, is this, direct overlapping of pure p orbital. So the sigma bond is in between the two nuclei. The one nuclei is here from one carbon, let's say. Another carbon is here, so the electron sits in between the two atoms, right here. Direct overlapping. In a pi bond, above and below. Okay? So once again, guys, in this, I'm gonna color code this. So in the blue sigma bond, what are the orbitals forming that bond? The blue sigma bond. Please type it on the chat. I want everybody participating. What are the orbitals making this sigma bond? It's an sigma sp2, sp3. Perfect. because this carbon is sp2 and this carbon is sp3. So that is perfect. Thank you for that. Okay, so let's see now the next thing that I want to go over. First, I'm gonna start by something slightly easier. I'm gonna look into this oxygen, the red oxygen, okay? What is the hybridization of that oxygen, guys? Of the red oxygen. It has a double bond, is sp3 hybrid, is sp2 hybridized, sp2 hybridized. Okay, sp2 hybridized means that there are, and I'm gonna write it over here once again, if this sp2 hybridized, so I'm gonna set oxygen is sp2 hybridized. So if it's sp2 hybridized, it means that that oxygen will have 3 sp2 hybrid orbitals and a pure orbital. That's what I mean by when I say that this oxygen is sp3 hybridized, sp2, I'm sorry. So when I said this oxygen is sp2, I am saying that there are 3 sp2 hybrid orbitals around this oxygen, and there is 1 p orbital on this oxygen too. Those are the 4 orbitals in the valence shell of this oxygen. So my question now is, and I'm gonna type it on the chat. I'm gonna pull this question because that's gonna help me to see if you guys are following. So in which orbital of the red oxygen are the lone pairs located? So in which orbitals of the red oxygen are the lone pairs located? Okay, so 26 people is still pending to answer. Please answer that question on the polling to make sure that you guys are following. Okay, that's fantastic. So everybody answered right. So both lone pairs are located in sp2 hybrid orbitals. Why? Because once again, there are 3 sp2 hybrid orbitals. One is used for this sigma bond here, and the other 2 for the 2 lone pairs. The pi bond is through the p orbital. So in that oxygen, I will have 1 lone pair in an sp2 hybrid orbital, another lone pair in an sp2 hybrid orbital, okay, and 1 sigma bond through an sp2 hybrid orbital. There is also 1 pi bond with a pure p orbital. Those are the 4 bonds of this, the 4 orbitals in the valence shell of this oxygen, because it's sp2 hybridized. It has 3 hybrid orbitals. So guys, what is the angle in between the lone pairs of oxygen? What's the angle in between the lone pairs of the exactly slightly less than 120, but that's okay. 120, perfect, because they are both in sp2 hybrid orbital. Beautiful. Okay, so All right, so here is now a new piece of information. I want everybody to pay attention, okay? Because what I'm gonna say now is new and it's gonna be very important for you for this class and for organic chemistry, okay? Okay, guys, at first, according to what we have discussed so far, what would be the hybridization of this oxygen here? I'm gonna color code it as blue. According to what it could be sp3, right? Because everything that we see is sigma bonds, okay? Right, so here is a new piece of information. I'm gonna type it here on the screen, okay? So everybody can write it. This is super important. Every atom with lone pairs next to a sp2 atom will also be sp2. Cannot emphasize this enough. Every atom with lone pairs next to an sp2 atom will also be sp2. There is a scientific explanation for this. You might not know or have all the knowledge that you need for that. You'll see that later on. But at least for now, I want everybody to understand that every atom with lone pairs next to an sp2 atom will be also sp2. Okay? Go ahead, Ruth.
Yeah, I just want to make sure there is no exception to it.
But that's the exception that I'm saying, because when I asked what is the hybridization of that blue oxygen, everybody said sp3, which makes sense because that's what I had thought so far. But I'm telling you now that that oxygen is going to be sp2 because it has lone pairs and it's next to an sp2 atom. Or you can, and you will see in some textbook also, is next to a double bond. It doesn't matter, it's the same thing, because if there is a double bond, this atom is going to be sp2. I like it with sp2 because it's more general, more scientific, okay? So Galina, an example of what? You have it right here. What is the hybridization of, according to what I just said, what is the hybridization of this oxygen, guys? This oxygen is going to be sp2. Why is sp2? Because this oxygen, and guys, this is so important because that's going to allow you to understand everything later on when we talk about resonance. And this is so important for the next semester. A carbon where? This is an oxygen atom. The carbon is here. This carbon is sp2. No, I'm talking about this oxygen. What is the hybridization of this? What is the hybridization of this carbon, guy? What is the hybridization of this carbon? That's an easy one. It has a double bond. It's sp2 hybridized, right? This oxygen and this carbon are both sp2 because they have a pi bond. So this oxygen with lone pairs next to an sp2 atom is also going to be sp2. And I'm gonna do something here. So this oxygen is gonna be sp2. So this is gonna be now the blue oxygen. So again, oxygen blue is sp2. The moment I see is I'm talking about an sp2 oxygen, I have to think about 3 sp2 hybrid orbitals and a p orbital. So I'm going to ask a question here and say, in which orbitals, and I want you guys to think the answer, okay? Are the lone pairs of the blue oxygen located? You know now already that is sp2. Okay, so that information is key to answer that question. So in which orbitals are the lone pairs located for the blue oxygen? Okay, Anastasia, so what's Anastasia, what's the hybridization of the oxygen is sp2, right? Okay, sp2. Aha. So let's see, let's do this together. Okay, so we said sp2, so it's gonna have 3 sp2 and 1 p, correct? Everybody agrees on that. So we assign sp2 hybridization, and because we assign sp2 hybridization, we can tell that there will be 3 sp2 hybrid orbitals and 1 p orbital, okay, around this oxygen. How many sigma bonds do we have in this oxygen? According to the drawing, how many sigma bonds? 2 sigma bonds, right? So one sp2 is going to be used for 1 sigma bond. Another sp2 will be also used for another sigma bond. I still have 1 sp2 and 1 p free. What is it left on the oxygen? Is there any other sigma bond? So only lone pairs. So which means that one lone pair, guys, is going to be in an sp2 orbital because that's what is available. And the second lone pair will be in a p orbital because it's sp2 hybridized. Okay. So once again, I'm going to repeat how I reason this because this is very important. So I said this atom is sp2 because it has lone pairs and it's next to an sp2 carbon. I assign the hybridization to be sp2. The moment I know it's sp2, I know that atom has in the valence shell 3 sp2 and 1 p orbital. That's a given. Okay, now I see 2 sigma bonds. So 2 sp2 will be used for these 2 sigma bonds. And what is left? 2 lone pairs. So 1 lone pair must be in an sp2 orbital and 1 lone pair must be in a pure p orbital. So what is the angle between the lone pairs of the blue oxygen? What is the angle between the lone pairs of the blue oxygen, guys? Okay, so I want you guys to look at this picture here. One lone pair is, so I'm gonna make it the drawing easier for you, okay? I'm gonna start drawing this atom for you guys here, okay? So I said that is sp2 hybridized. It has 3 sp2 orbitals. Therefore, we can say there are 3 orbitals, 3 sp2 orbitals with a 120 degrees angle. Everybody agrees on that? And the fourth is in a pure p orbital. There is a p. Okay, so once again, 4 sp2, 4 orbitals, 3 sp2, the molecule is trigonal planar, and 1 p. So this is sp2, This is sp2. This is sp2. 3 sp2 and 1 p. That's what it means. So once again, what is the angle in between? So one sp2 is for a sigma bond. The second sp2 is for another sigma bond. The third sp2 is going to be for a lone pair. So what I'm going to do for you guys to see that better, I'm going to draw a lone pair here. So everybody knows that, and I'm going to color code the lone pair. Okay. So what is the angle in between the p orbital and the lone pair? Okay, what is the angle in between the, I'm gonna ask another question. What is the angle in between this p orbital and this sigma bond, guys? 90 degrees, right? Everybody understand that because that's the concept of a trigonal planar structure. The angle in between the sigma bond and the p orbital is 90 degrees. Look at the structure here. This is an sp2 trigonal planar. 120 here, 120, 120, the pi above and below, right? So that's how it's like saying this. The angle in between these two, I'm gonna color code it so you can see better. This is the p orbital, right? This is the hybrid orbital. The angle in between the hybrid and the p is 90 degrees, right? So what is the angle in between the two lone pairs then? If the lone pair is an sp2 hybrid orbitals, what is the angle in between the two lone pairs? One lone pair is in the pure p orbital, one lone pair is 90 degrees. The angle in between the two lone pair is 90 degrees because one lone pair is in a p orbital and another lone pair is in an sp2 hybrid orbital. Okay, so the angle in between these two is 90 degrees. I'm gonna make it bigger for you guys so you can see, okay? 90-degree angles. So summary of this last part before we end today's class. Any atom next to an sp2, any atom with lone pairs next to an sp2 atom is sp2 hybridized as well. This is very important, guys. I will repeat again next class, but I want you guys to start digesting this, okay? Because this atom is sp2 hybridized. I know it has 3 sp2 and a p orbital around it in the valence shell. In the valence shell, there will be 4 orbitals. 3 will be sp2, and the 4th will be p because it's sp2 hybridized. Now, what are the 3 sp2 hybrid orbitals used for? 2 of them will be used for sigma bonds. 1 for this carbon, 1 for this carbon. 2 sigma bonds. 1 sigma, 1 sigma. And the remaining sp2 and the remaining p will be for the lone pairs, which means that one lone pair is here in a pure p orbital, and the second lone pair is back here in a hybrid sp2 orbital. Therefore, the angle in between these two is 190. I'm sorry, it's 90 degrees. I'm gonna see if I can write it over here. Here you go. So the angle here is 90 degrees. Okay. Any questions, guys, in regards to this? We will go over this in the next class because I really want you guys to understand this very well. It's very important. You're gonna be using this a lot, not only this semester but also next semester. That's why I want to take time to make sure that everybody really understand what I'm talking about. Yes. This carbon here is trigonal planar. I'm gonna draw an arrow so you can see. because it's sp2 hybridized. Okay. Trigonal planar is this. So the 3 sigma are 120 degrees from one another in the same plane. And the P is perpendicular to the plane. You can even do, for example, this. Okay, so 1 sigma is on the plane of the screen, another one is coming toward you, the third is going behind the screen. They are all in the same plane, 120 degree. The p orbital is on the plane of the screen, literally. Okay, so the angle in between the p orbital and the sigma bonds is gonna be, of course, 90 degrees. Because one of the lone pairs is in one sp2 hybrid orbital, the angle in between the two lone pairs will be 90 degrees. What's the shape of the whole thing? I'm gonna hope for, I'm gonna hold to answer that question for later on, Rachel, but the shape is trigonal planar, all this, and you will understand why later, okay? I want you guys for now to understand this first. We'll go over that later, but this whole section will be trigonal planar. Flat, all this area. Okay, any other question, guys? Go ahead, Noah.
Can you hear me, Professor?
Yes, yes. Go ahead, please.
This is about your office hours, like on Thursday. Do I have to schedule an appointment, or is it going to be an open meeting?
It'll be open. I'll post the link. I'll post the link on Thursday morning.
All right, thank you.
Thank you.
All right, have a good day.
Thank you, you too.